before had introduced the Brayton cycle, and we talked about regeneration, reheat, and intercooling. Should I do a quick review of those, or are you okay with that? Do you understand when somebody says Brayton cycle with regeneration, what that involves? Brayton cycle with reheat, and then Brayton cycle with intercooling. Normally these go together, intercooling and reheat, but this can be by itself, with or without regeneration. All right. So we also want to contrast the Brayton cycle with two other cycles. One is the Ericsson cycle, and one is the Stirling cycle. Now, there's not a lot of power production, or much at all, associated with Ericsson or Stirling, although you can buy a little Stirling engine and run it on your desk with a little flame and a little heat source, okay? And you can do some YouTube searches or internet searches and find demos and build something that'll run on these cycles. But the main power, like jet engines and natural gas turbines and propulsion systems and power plants, natural gas power plants, they're the traditional Brayton cycle with those enhancements we already talked about. But we'll introduce the Ericsson cycle first. It's named after this man, John Ericsson. You can see the years that he lived. He was a Swedish-American inventor and a mechanical engineer. If you go to Washington, D.C., you can see on the National Mall a memorial for this man, John Ericsson. And so right there's the Potomac River. This is prime real estate. This is a very noteworthy accomplishment to have a national memorial erected in your honor. Also, if you go to New York City, you can go to Battery Park. You can see a large statue, here it is, of this individual, John Ericsson. And this in his hand is an image of the ironclad, the USS Monitor, which was launched in 1962 in the beginning part of the Civil War. And that changed naval warfare from that day on, when it went out and battled. The Monitor and the Merrimack battled. It was a draw. They slugged each other with cannonballs but they continued to bounce off. A wood ship would have sunk. So wood ships were obsolete from then on. Ironclads were the way to go. He also put steam engines in boats. He did a lot of things, not just the Monitor. He did a lot of stuff. He was a very creative individual. So what about this Ericsson cycle? Well, it's really an extension of the Brayton cycle. So if we remind ourselves, what is that Brayton cycle? It starts with adiabatic compression. Let's go ahead and sketch that again, the Brayton cycle, on a temperature entropy diagram. So if I start here and I do adiabatic compression, I jump from a line, well, let's follow it out. Isobaric heating, then adiabatic expansion. Because it's adiabatic and reversible, they're isentropic, straight up and down. And then isobaric cooling. So this line right here is a line of constant pressure. This is a line of constant pressure, true? So that's the Brayton cycle as described, with 1 to 2 to 3 to 4. Well, what happens when we had Brayton cycle with an intercooler? And we didn't have to take it up to that high pressure. We stopped at this intermediate pressure because these lines are like lines of constant pressure. And we cooled it along that line of constant pressure back down to the ambient temperature. And then we compressed it again. So we had 2 stages for our compressor and 1 intercooler. And now we're on this line of constant pressure. And now we go from this new 2 all the way up to 3. That was 1 intercooler. What happens if you'd have 2 intercoolers? Well, I would take it to some intermediate pressure, then another intermediate pressure, so it's like I could divide that pressure difference up into thirds. So I'd pressurize, cool, pressurize, cool, pressurize, and go forward like that. Well, as you continue to add more and more intercoolers, What does the compression, when you're trying to go from this low pressure to a high pressure, what does that line become like? It becomes like this, straight across. If you had a large number of small compressor stages mixed with intercoolers. So what happens is the Brayton cycle with intercooling, when you have a lot of intercooling, multiple intercoolers, it becomes isothermal compression versus adiabatic compression. You're compressing at constant temperature, and that's good for performance. Let's look at the other end of the cycle. Because you had reheat, what you do is, if you just had one reheat stage, you'd expand to some intermediate pressure, and then reheat it, and then you'd be back up here. Then you could expand down to this other pressure, right? And now you continue. So that's two turbine stages with a reheat in between. See how that works on a TS diagram? Let's say you had 3, so it'd probably bust it into thirds on the pressure. You'd expand, reheat, expand, reheat, and then expand, and then continue down. Well, what happens if you have multiple reheats? Well, state 4 moves from here to here to here. It'll move all the way up to here, and now I'll have isothermal going from state 3 to state 4. True? On a temperature entropy diagram. So state 2 moved from here all the way down to there. So that's the change from the Brayton with no intercooling, no reheat, to multiple intercoolers and multiple reheat stages. So you have, this is now isothermal expansion, just like you had isothermal compression. So the Ericsson cycle is like a Brayton cycle with that multiple intercooling and multiple reheats. Is this better for performance? Yes, it is. It's better to compress a gas at low specific volumes. When it gets hotter, it's larger specific volumes. So it'll cost less work per unit mass to compress it isothermally, and you'll get more work per unit mass as if you expand it between those two pressures isothermally. So it's better for performance. There's another cycle. It's called the Stirling cycle, and what I thought I'd do is emphasize, just remind ourselves of the Brayton. Here it is. Sketch it not only on a TS, but also sketch it on a PV diagram. Okay, so you start at state 1, you compress, then you go to isobaric heating, then you expand, then isobaric cooling. So if I wanted to put state 1, state 2, state 3, state 4, what's between state 1 and state 2, 2 and 3, 3 and 4, 4 and 1, you see these isobaric constant pressure lines between the 2 and the 3, and the 1 and the 4. All right, so 1 to 2 to 3 to 4. What about Ericsson? Well, we just sketched that one. Start at 1, isothermal compression, followed by the constant pressure. This is a P equal to a constant, pressure is equal to constant, pressure is equal to constant. Heating, isothermal expansion from 3 to 4, back down to 1. True? So this line right here is pressure is equal to constant. What does that look like on a PV diagram? Well, we'll start, instead of going where from 1 to 2, was this a line of S equal to a constant from 1 to 2? Isentropic? Yeah. So instead of that, it'll be like this to 2. Now, I didn't show them on the same diagram, but if you sketched S is equal to a constant, it would be steeper. So, but this line right here is temperature is equal to a constant from 1 to 2, okay? But both of those 2's are at the same temperature if I'm trying to contrast Brayton with isentropic compression from 1 to 2 versus isothermal compression from 1 to 2. Now we go out constant pressure isobaric heating until we get to a point where you bring it down, isothermal expansion, it's not as steep, and there you go. So that's 1, 2, 3, 4. Did that help? Now the Ericsson, let's just sketch it out. It's isothermal compression, so it looks like 1 to 2 on the TS diagram, just like the Ericsson cycle, true? Isothermal compression, but now it's isochoric heating from 2 to 3. Isochoric, what does that mean? Constant volume, right? Constant volume. And it takes you a while to visualize, but we have a line of constant pressure, and then we have a line of constant volume. The line of constant volume is going to be steeper. So I'll try and show it scooting up. It's going to be steeper instead of a line of constant pressure. This is just to kind of give you a visual representation. Pressure is equal to a constant versus volume is equal to a constant. So just so that you know it's steeper, now we get rid of it so it doesn't clutter up the diagram too much. And then we go through isothermal expansion and then back 4 to 1. True? How about on a PV diagram? Isothermal compression, so 1, 2, 2. And then what about isochoric heating? Where is state 2? Straight up, that's right, to 3. And then isothermal expansion followed by isochoric cooling 4. 1 to 2 to 3 to 4. Did I do that right? Thumbs up if you agree. Okay. Now, if I sketched a true Carnot cycle on a temperature entropy diagram, what does it look like, a true Carnot? I mean, there's no false Carnot. I'm just saying the Carnot cycle on a temperature entropy diagram. A box, a rectangle, true. And so it's straight, 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 straight. True? Yeah. Which one of these TS diagrams look closer to the Carnot? The Stirling. It keeps pushing. It looks closer. So the thermal efficiency of the Carnot is the highest you can get between two thermal reservoirs. True? You fix the high temperature, you fix the low temperature, you can't get a higher thermal efficiency than 1 minus TL over TH. Will the Stirling cycle, Ericsson cycle, or Brayton cycle thermal efficiencies be as high as a Carnot? They can't, and they're really not, because they're not the same. All the heat doesn't come in like that at the same temperature and then rejected, and what you do is 1 to 2. So these are very high efficiency cycles, but they're not as efficient as a Carnot. Let me ask this question. Why don't we have more Ericsson cycles and more Stirling cycles out there in the real world? Because it's really hard to do isothermal compression or isothermal expansion. When something is isothermal, and yet it's being compressed or heated or expanded, how does that happen? You have to be adding heat or removing heat. We build devices like a compressor. It has one purpose. It compresses. Another device called a heat exchanger, it's designed to transfer heat. You look at a compressor and you look at a heat exchanger, they don't look alike. They have different functions. It's hard to make them into one device where it's a great heat exchanger and a great compressor. So that's very difficult. That's why we had it in stages, where you'd have a compressor stage followed by a heat exchanger, followed by a compressor. So trying to go toward isothermal compression and isothermal expansion is good. That's why we had the Brayton cycle with those reheats and intercoolers. They are implemented in practice. It's just to get an infinite number of them, it becomes too complex. So there's really no Ericsson and Stirling cycles out there in practice like there are Brayton cycle gas power engines. Let's take a look now at combined the gas as well as a vapor power cycle. So here you'll bring in air, put it through a compressor, through a combustor with some fuel, put it through a gas turbine. Some of that's connected via the same shaft. Some of that power from the turbine goes back to drive the compressor. And then you do something, you put the exhaust gases through a heat exchanger where you're transferring heat out of those exhaust gases and are heating up, acting like a steam generator for a steam. So here's your gas cycle, and here's your vapor cycle. And so this heat exchanger boils water, creates steam, pass that through a steam turbine. After the steam turbine goes through the condenser, pump, and back. So we're very familiar with the vapor as well as gas power cycles, so they combine them to try to improve the overall efficiency of the system. Let's say somebody asked you, said, this is a complete system. Let's introduce states. Let's call them state 1, state 2, state 3, state 4, state 5. So those are state 1, 2, 3, 4, 5 are all for the gas power, all for air properties. And then state 6, state 7, state 8, and state 9 are all for water or steam. So state 6, 7, 8, 9 are for steam. And you're asked to compute something like what is the overall thermal efficiency of this power cycle? Well, you would want to know the power that comes out of the gas part of the cycle, add it to the power out of the vapor part of the cycle, VAP, which is W dot VAP will be what comes out of the steam turbine minus what has to go back to drive this pump, true? So that's what comes out of the vapor, the net out of the vapor cycle. And then what do you divide it by for the thermal efficiency? Q dot N? Q dot N. And where is the only Q dot N? It's only in the combustor, that's right. You look and you search, where are all my Q dots? There may be some Q dot outs, okay? But the Q dot Ns are just, there's only one place where there's a rate of heat transfer in. All right, let's do this. How do I calculate Q dot N? Would that be the mass flow rate of the gas or the air? You could put M dot A or M dot G. You know, it's what symbol you want for the mass flow rate of the air or the mass flow rate of the gas, times the enthalpy 3 minus enthalpy 2. Does that look reasonable? How about the W dot for the gas cycle? Would that be the mass flow rate of the gas times the specific work out of the gas turbine, H3 minus H4, minus H2 minus H1, what has to go back to feed the compressor? Does that look good? Okay. How about for the W dot of the vapor? Is that equal to the mass flow rate of the steam times what is produced in the steam turbine, H7 minus H8, minus what needs to drive the pump, H6 minus H9. Thumbs up if you agree on that one as well. So it depends on the enthalpies and the mass flow rates. Because we have two mass flow rates, the air and the steam, then we have to link them together. Where are they linked? They're linked together in this heat exchanger, true? So what comes, the rate of heat transfer out of the air in that heat exchanger is equal to the rate at which it flows into the steam in that heat exchanger. So the equation that links these two cycles, the gas and the vapor power cycles together, is the energy balance right here, which is the mass flow rate of the gas times the enthalpy 4 minus enthalpy 5. Isn't this so many kilowatts coming out of the gas, equal to the mass flow rate of the steam, H7 minus H6. Do you agree? Does that look good? Very good. Well, let's take a look. Somebody says, I would like to do this. I would like to do W net out of that cycle is equal to Q dot net in. Can I do that? Do you understand that? Have you solved enough of these problems where they say, well, we could go ahead and get W dot net, but it may be easier to get Q dot net. And because the W dot net was, you have to account for this part, and then depending how you do the turbine, you could do the turbine out only minus what goes back to drive the compressor or this part. But if you decided to use Q dot net, well, I need all of my ins as well as outs. So it's going to be Q dot in, there's only one of them, minus any and all Q dot outs. Where do I have some Q dot outs? The condenser, the steam condenser. So this is the one of those Q dot out in the condenser. Okay, so you would need to put that in here. Is there any other Q dot out? I ask this question because it's tricky. And a lot of students will want to go this route and then they'll make the error right at this point on an exam. Yes, sir.
Okay, so just to be clear, right? The heat exchanger, the heat that is being exchanged is from the gas cycle into the vapor cycle.
That's exactly right. And we would call it an adiabatic or well-insulated heat exchanger.
So that's why they're equal.
They're equal because there's none to the surroundings. It's all internal. You got it? Yeah, from 5. And people will forget it because it's not shown explicitly. Conceptually, what you have to do is you have to bring 5 and put it through a heat exchanger to get it back to 1 to close the loop. And to close that loop, you have some Q dot out of the air. I mean, whatever symbol you want for that entity. But this is, by an equation, is equal to the mass flow rate of the gas times the enthalpy 5 minus enthalpy 1. Now I have a complete Q. I've tracked everything for the Q. Okay. All right. Very good. Thank you. Well, here's a problem. And if you followed what we just did on that other slide, then this is very straightforward. So I have a combined gas turbine vapor power cycle. State 1 is the beginning. So state 1, 2, 3, 4, 5, they're all air. And then 6, 7, 8, 9, that's all steam. And you're given pressures and kPa. A lot of times with the air, we like to work in temperatures and K, but in steam, we like to work in temperatures and in degrees C. So I have 2 temperature columns to keep them straight. And then the big one is I need all those enthalpies, true? Need those enthalpies for the air as well as for the steam at different locations. How do I calculate them? Looks like we're considering this PR column. That's at pressure for isentropic processes in the air table. So we're counting for variable specific heats for air. And, oh, it looks like it goes from 1 to 2s and then 2 to 2 actual. So there's some isentropic efficiency of the compressor. But if you're just given the properties, Somebody's done a lot of work already. Likewise, from 3 to 4S and then 3 to 4 actual, that's expansion through the turbine. Looks like there's some isentropic efficiency for that turbine, the gas turbine. And then from 7 to 8S, 7 to 8, that looks like expansion of the steam through the steam turbine. And then 9 to 6S or 9 to 6, that's the pump with some efficiency for the pump. So you can get a lot of states and a lot of calculations to get a table like this, but I need those enthalpies to answer a question like, what is the net power in megawatts developed by that power plant? Where they tell us not only the states, but that the gas turbine produces 150 megawatts. So they give us that W dot of the gas cycle is equal to 150 megawatts, which is the difference between what the turbine produces and what because it's all connected on the shaft, the compressor part consumes. And we worked out that equation, which was the mass flow rate of the gas times enthalpy across the turbine, 3 minus 4, minus the enthalpy across the compressor, 2 minus 1. W dot gas. So knowing W dot gas, I know all those H's. The only unknown is the mass flow rate that's going for the air. True? You can use that to then come in and get the mass flow rate of the steam from the energy balance around that heat exchanger. The heat exchanger that linked the gas and the vapor power cycles together. This was H7 minus H6, M dot gas, H4 minus H5. And so now you can calculate the mass flow rate of the steam because you just calculated the mass flow rate of the gas. Once I know that, then we calculate W dot vapor net is mass flow rate of the steam. The work or the power out of the steam turbine, subtract off, I didn't leave enough room there, for the pump. Does that all make sense? So now that I have the power out of the vapor power cycle, the net power developed by the entire plant is what comes out of the gas cycle, 150 megawatts, and what is produced by the vapor cycle. That's exactly right. So this steam is in a two-phase region here, and what comes out of the condenser at state 9 that goes into the pump is saturated liquid. So this is saturated liquid 0 right there. And then compressed liquid at state 6. And then this is superheated vapor at state 7. And then two-phase. They're just a Rankine. You're combining the Brayton gas with the Rankine vapor cycle. So that's how you answer for part A. And then the overall efficiency, you just have to calculate Q dot into the cycle. The only place it comes in is in the combustor where you burn the natural gas.
What happened to the fuel? Because you said like you had a fuel source coming in with your gas.
Right, and to account for the CO2 and the H2O, we do an air standard analysis, which says it's just pure air. And so even though I showed the fuel there in the illustration, we don't have the tools at this point to do a good job of analyzing it. It can be more complex. And so this was the mass flow rate of the gas times, what is it, enthalpy 3 minus enthalpy 2. And then the thermal efficiencies, the W dot plant over Q dot into the plant. A lot easier if they give you a table of properties, but otherwise you have to look them all up and chug through all the calculations. let's talk a little bit about where you might find a combined cycle power plant. Does the city of San Antonio, CPS Energy, does it own any of these? First of all, I found this interesting fact. You know, I thought that the city of San Antonio purchased or constructed City Public Service Energy, CPS Energy, a long time ago, but it was only in 1942 that they actually purchased a local utility and then renamed it, called it City Public Service. Probably a really smart move, guaranteed smart move back in 1942. Because right now, CPS Energy funds a lot of the city budget, a lot. And so I mentioned it is the largest municipally owned electric and gas utility company in the nation. That's very distinctive. They have some of the lowest rates throughout. But when you have hydroelectric that's funded by the federal government who made dams, you can't beat with that. I mean, that's just cheap energy. So Tennessee and Washington State have really low electric utilities. But if you live in Hawaii, guess what? There's just not a lot of oil or natural gas wells in Hawaii, and so it's very expensive. So that price of electricity does vary significantly throughout the United States. Houston is a lot higher, and certain other places are higher. California is higher. Okay, and it has a good mix of fuel. 47% by this article was coal. 32 is nuclear. Where do we get the nuclear from? 32% of this electricity being used on an annual basis in this room is produced by nuclear. That's a lot, isn't it? In the homes that you own and run, or apartments that you use. It comes from the South Texas project down by Bay City. And a number of graduates from UTSA, mechanical and electrical engineering, are working down there at those plants, helping continue to run those big power plants. 12% gas and 9% renewable, and they have a goal of having more and more changing over. About 10 years ago, they built the first combined cycle plant in CPS did. The lead engineer for it was a UTSA grad for that project. Also, they've continued to expand, and in 2012, April, they finished buying out a power plant in Seguin. And this power plant is a 800 megawatt combined cycle natural gas. So they're burning natural gas as a primary fuel, but they also have a vapor power part to make more electricity, squeeze more of that energy and convert it into electricity. So this is fairly recent. Looks like they picked up all the plant employees, which I'm sure they were happy for. That plant's been out there since about the 1980s. Where is it located? Well, here is I-10, and you're going around the city of Seguin. You cross over the Guadalupe River. If this gives you any landmarks going toward Houston, this is toward Houston, true. This is toward San Antonio. There's a metal recycling plant that does that. They changed the name a couple times, but a lot of UTSA grads work there too. Scrap metal is turned into rebar. It's CMC, yeah. And so if you're from that area and you want to get a great job, check it out. Also, Caterpillar has a big plant now in Seguin. Alamo Industries has a big plant. I've known students work there. Motorola has a big plant. A number of graduates have and are working out there. So there's a lot going on in Seguin. Anyway, as you drive a few miles past after you cross the river, and you'll see it, it's plain as day sitting right there. So that's what they purchased. Anybody remember seeing it? Couple? Good. And a number of UTSA grads have gone and worked in different locations, and I suspect some of those employees could be that I just don't know them, but they could be graduates, because engineers do work in plants like that to keep them running. Also, I remind you that the integrated gasification combined cycle power plant CPS bought into, and it's a 400 megawatt cycle plant, and CPS Energy is committed to purchasing 200 megawatts of that. How big was this one out in Seguin? 800 megawatts. So it's pretty big. It's a pretty big plant. And so you can learn more about that. Did anybody go and check out that website? I think I showed this once already, haven't I? This semester? You can go check that out. The integrated gasification, you know, as you want to do more and extract more and have cleaner energy, it becomes, the power plants become more engineered, highly engineered. And I don't think I showed this illustration, did I? Let's talk through it real fast. The one out there that is a 400 megawatt plant, it's out by Odessa, and it's quasi-experimental. There's a large part of it's funded by the U.S. government. But they bring in coal, not natural gas. That's the primary fuel source. And they go into a gasifier, and the purpose of the gasifier is to make something like natural gas. They call it syngas or synthetic gas. Syngas. It's like natural gas. So to make it out of coal, they need a pretty pure oxygen stream. You're going to get the oxygen from the air. So they put it through a compressor, then they try to pull off the nitrogen. They have a separation unit. You put in an oxygen stream with the coal, and you put in steam, H2O, water, steam, just like that. So you need source of steam. And then they have solid waste coming out of the gasifier. But this synthetic gas comes up, and this is one of the keys or the beauties of that plant. They can do a lot better job of cleaning it up and getting out any sulfur or any mercury that may be in there, which is important to the people that live downstream of these plants. They don't want that emission of mercury and sulfur. Although the mercury and the sulfur emissions are much, much, much lower than they used to be, they're still cleaning up some particulates. Now you have a gas that goes into the combustor, that passes then through the gas turbine, and so this is your traditional gas power cycle. So air, compressor, combustor, gas turbine, heat exchanger, and then you just exhaust this warm gas. In that heat exchanger, you make some steam. Some of that steam is routed back to the gasifier, and then some of it is passed through the steam turbine, condenser, pump, boom, and you have your vapor power cycle. There's a little makeup water because you're using steam. So this power plant, I don't have any updates. Did anybody check it out and see if they're still on schedule, coming online? But you could find out information about this one out in Penwell, Texas, the Texas Clean Energy Project.